Hello, sir. How is sir? Hello, Indranath, sir.
Hello, Sarkar, I am audible.
Yes, listening, sir. Can I start, sir?
All have joined.
Yes, already someone is joined and someone is after starting also they are willing, they are starting to join also.
Because it is 10:12 at my end. I don't know what is the time at your.
Like that.
It is 10:15, na? And hope the time is given from 10:30.
Yes.
Okay, if you want, I can wait till 10:30. No problem.
Okay, sir. Then 10:25 we can start, sir.
10.
10:25.
10 minutes you wait, sir.
Sure. After 10 minutes. Yes.
Okay.
ఎవరు వినట్లేరు కాలేజ్కి వచ్చిన వాళ్ళని.
Yeah, Isha madam. Isha madam.
Yes, sir, I'm ready.
You can start, madam.
on
Okay,
the
I can start.
start.
Am I audible, sir?
Yes, yes, you can audible, sir, madam.
Okay. Okay, sir.
Indranath, sir.
Yes.
Yeah. Good
Sir,
morning,
we
Speaker.
are starting, sir.
Yeah.
Good morning, Speaker Dr. Indranath Sarkar, all participants, and my dear faculty friends. On behalf of Vignan Institute of Management and Technology for Women, we welcome you all to the fourth day of Faculty Development Program on Microstrip Patch Antennas. I am Usha Rani, working as an assistant professor in EC department. It is a great pleasure and honor to introduce today's speaker, Dr. Indranath Sarkar. He is presently working as an assistant professor in the Department of Electronics and Communication Engineering at JS College of Engineering, Kalyani, West Bengal. He has completed his PhD in radio frequency engineering in 2013 from University of Kalyani, West Bengal, and Masters of Engineering in Telecommunication Engineering from Jadavpur University in the year 2002, and Bachelor of Engineering in Electronics and Telecommunication Engineering from NIT Durgapur. His area of research is microstrip antennas, FSS, and artificial neural networks. He has 20 plus years of experience in teaching. He has been the editor of Springer lecture notes in bioengineering entitled Advancements in Medical Electronics. And he also published 30 plus research papers in various reputed journals. Good morning, sir. Now I request you to take over the session.
Yeah, good morning.
Yeah, good morning. Welcome, sir.
Is my screen is visible?
Visible,
Hello?
sir.
Okay.
It's visible.
Yes, sir. Visible, sir.
Visible.
Visible, sir.
Thanks for nice introduction. Mr. Shaviran Chatterjee, who is the coordinator today, he is also a pass out from our college. So I'm very glad to be invited here for today's presentation. So I'm starting this presentation on microstrip patch antennas. The points to be discussed today are the introduction part is there, research trends of microstrip antenna design part, and the recent investigations on microstrip antennas which has been carried out in the laboratories. Now, regarding the introduction, these are the points to be discussed today. Normally, we know microstrip patch antennas, the common structure look like this. Normally, there are PCBs are utilized for the microstrip patch antenna design. And these PCBs are a special PCB, which are having a very low loss, the low loss tangent, as well as the radiation pattern should be appropriate. Such PCBs may be the glass epoxy PCB, which is available in the market, but the lossy factor is more. That is why for the research purpose, if we use, it will not be sufficient for commercial uses. So that is why we normally use the microwave PCB, which are expensive, but the loss tangent is very low. So the front view and back view normally given in this way, it is shown. So this is the front view and this is the back view. Normally, microstrip patch antennas are having two number of ports, that is two number of lines. That is, one is the ground line, another is the main line. That is, the signal is fed to the patch. So this is the top side, which is known as patch side, and the bottom side is the ground side. So with reference to ground, the signal is fed to the patch. And normally, this type of figure we already have seen in various papers in which the patch is compared with the size of the coin. Since the patch antennas are of very small size, So that is why it has been compared with sometimes scales where it is showing that it is of millimeter length, and sometimes it is compared with the coins. And this is very much important. This is the three-dimensional radiation pattern, which shows the amount of radiation power in a particular direction. That means it is a 360-degree pattern. So in which direction, what is the amount of power, how it is radiated? All these things are very much clear from the 3D radiation pattern. And from this, we are calculating various types of parameters for the antenna so that it will be applicable for commercial purpose. And it is a typical simulated configuration in which the power is shown, that in which direction, what is the amount of power is radiating on the right-hand side. Normally, 2D radiation pattern may be utilized for these parameters. These parameters are very much useful because whenever we are interested about antenna, we need the power to be radiated, and the directions are also very much important. So for this, normally beam width between the first null, which is given by this equation, are very much related to the half power beam width, where half power beam width can be calculated from the origin to this side. So there will be some subtended angle, and that gives us the half power beam width. And the side lobe levels should be less or equal to 20 dB for the satellite and high power applications. So these are the typical values which are shown for type of applications. So depending on the applications, these values are changing. The directivity is also one important parameter for the microstrip antenna. Similar to other antennas, the directivity is nothing but the ratio of the maximum radiation intensity to the average radiation intensity. And here, a small pictorial information shows us which is the maximum amount of radiation intensity, which is related to the product of the directivity and the average radiation intensity. So in this way, we can find out one important parameter, which is known as the directivity. That is the amount of power radiated in a particular direction with reference to other directions. The orientation of the radiated electric field vector is also another important parameter, which is required for microstrip antenna as well. So here the orientation, if it is linear, if it is following the linear path, then it is known as the linearly polarized signal. Sometimes we need the circularly polarized signal for specific application. At that point, we need the electric field vector tip should be should have a rotation of circular path, and if it is following, if the tip of the electric field vector is following the elliptical path, it is known as the elliptically polarized signal. So depending on a certain type of application, we need sometimes linearly polarized signal, sometimes circularly polarized signal, sometimes elliptical polarized signal is sufficient. So these are the various types of orientation of the tip of the electric field vector. Axial ratio is also another important parameter for the microstrip antenna, where the axial ratio is the ratio of the major axis of polarization to the minor axis of polarization. And a typical plot, as we see on the right hand side, the axial ratio, it shows the 3 dB, it shows the calculation possible for the 3 dB values. That is 3 dB cut point if we take from the left side to right side, it is giving here typically 380 megahertz, and which is 13% bandwidth. So this axial ratio is very much important to determine whether the polarization is circular or linear or elliptical. So as shown, axial ratio equal to 1 shows the circular polarization. Similarly, axial ratio more than 1 and less than infinity is known as the elliptical polarization. And if the axial ratio is almost equal to infinity, then it is known as the infinity means it is very high value, then it is known as the linear polarization. And normally we are finding the axial ratio bandwidth with reference to the 3 dB cut point. So whenever AR is less or equal to 3 dB, we are getting some cut point on the on this plot, and we are finding out the bandwidth of axial ratio. Now the point comes why microstrip antennas are important in today's research. Today we are finding that microstrip antennas are gradually are of more importance of research. It has been started long back, almost 30 to 40 years ago. It has been started to grow interest, and gradually, day by day, the interest to microstrip antennas has not been decreased ever. Many things has been fluctuated, but the interest in microstrip antenna are gradually growing, and still it is growing because the miniaturization devices. The devices also using tools are- Hello.
Hello.
Hello? Background, there is lot of noise, sir. Not able to understand. I think someone has unmuted their audio. Unmuted their audio, sir.
Hello, Samiran. Hello, Samiran, sir.
Yes, sir. Yes, sir.
Sir, mute all the
Yes,
mics.
sir, I unmuted.
Mute.
Hello, audible?
Sir. Audible.
Sir, audible, sir.
Yeah, thank you. So microstrip antennas, why microstrip antennas is an important part of the discussion, which is requiring that why should we concentrate on microstrip antenna? Because it is gradually growing interest because of the miniaturization of the devices. Gradually devices are miniaturized. That is why the components required for the implementation of those miniature devices are required to be small. And microstrip antennas are, as we already have shown, that it is compared with small coins, small millimeter scales. That is why microstrip antennas are always a small antenna, and thus microstrip antenna finds a great application in those miniaturized devices. So therefore, and it is based on the thin metallized patch, as we are constructing using the thin metallized patch on low loss grounded dielectric substrate. Now, what are the merits? These are the merits. That is the low cost and ease of manufacturing using printed circuit technology. That means usually we are constructing these microstrip antennas on PCBs, and these PCBs are low loss PCBs, which are not similar to the glass epoxy because it has some parameters which are reducing the loss so that the radiation pattern will be emphasized. Lightweight as well as thin profile, easy integration with associated microwave circuitry, easy to mount on conformal to the surface application. The surface may not be planar. It might have some curvy nature of the surface on which we need to install this microstrip antenna. So whatever is the surface configuration, it is very much conformal to any type of surface. So that is one of the great advantage of microstrip antenna for today's interest. Still, there are many demerits. Some demerits uttered earlier, now it is not uttered, which is called the narrow bandwidth due to the intrinsic high Q resonator action. So it has been overcome in various papers in last 10 years. The narrow bandwidth has been overcome for microstrip antenna. We can prepare broadband antenna using microstrip antennas with some modifications with earlier designs. So therefore, the first demerit may be recovered with various new configurations proposed. And thereafter, the losses in the dielectric, here the losses could be reduced in the dielectric from the manufacturer end if manufacturer takes sufficient precaution for the designing of the microstrip on the PCB. That is for the PCB production, if manufacturer puts attention, he can reduce the loss in the dielectric. It is not in the researcher's end. It could be reduced by the manufacturer. And coplanar feed lines and the generation of the surface wave in the air dielectric interface reduces efficiency. So these are the points which needs attention for the researcher who is preparing the microstrip antenna needs to take some precautions so that such interference could be reduced. And still there are polarization impurity which cannot be avoided. We need some protections. Now the materials required for the microstrip antennas are the printed circuit board, as we already have seen that PCBs in the market also we have seen. So they are glass epoxy PCB, but for the microstrip antenna we need this type of material that is which is having low loss looks like PCB, but it is known as sometimes called microwave PCB because it is specially prepared for the microwave device purpose. And also there is sub-miniature A type of this port, which is known as SMA port. So female SMA port are popularly used for our microstrip antenna design. And here it is showing 2-hole. Similarly, there are 4-hole such port is also available. So that depends on how many screws are required to mount this port on the PCB. And these are the straight SMA connector, right angle SMA connector. So all are nothing but SMA connector, but depending on the surface on which we want to connect this type of port. So depending on the flexibility of the surface, we need several types of SMA connectors. So these are not limited, but there are many varieties available in the market. We can Google it to find out such different SMA connectors. And here another important part is the materials for the printed circuit board. As I already discussed that the losses required to be reduced for the printed circuit board. So FR4, which is the FR stands for the fire retardant. These FR4 are the popularly used PCB, which are used by many researchers and of the order of 3.8 to 4.7 dielectric constant. It is available in the market. And in many research papers, we have seen that 4.4 is popularly used by the papers, research paper publications. So 4.4 dielectric constant is very popular for this type of microstrip antenna design. But also other configuration, the other values of the dielectric constant, such as the 4.0. Here is also 4.4 for polyimide resin with aramid basis. And 2.2 to 10.2 is available for the PTFE high frequency. So PTFE is also another important substrate, which is also popularly used in various research papers, which is the high frequency laminates are used in PCBs that require the low dissipation factor, DF, and very stable dielectric constants. And also Rogers 3.5 dielectric constant, 3.4 dielectric constant by the DuPont or Tyflex also very popular. Now, regarding the applications of this microstrip antenna, there are many applications, out of which these are important, such as the mobile and satellite communication application, in which the circularly polarized radiation patterns are very much used. And also it can be realized using either a square or circular patch with 1 or 2 feed points. Also, global positioning system application nowadays, it has a great use in case of all type of mobile devices, in which we see that the high permittivity substrate sintered material are utilized for the global positioning system. And these antennas are circularly polarized, very compact as well as expensive due to the positioning. There is also radio frequency identification application. So all these applications are made depending on the present day. The present day application, these applications highlighted. So RFID system is a tag.
Hello, Samir sir.
Utilized.
Yes, sir.
Mute mic, sir. All. Sir, Indra.
Yeah.
Yeah. Sir, your mic, sir. Sarkar, sir. Sir, Indranath Sarkar, sir. Your mic.
Yes.
Yeah. No.
Okay. So RFID tags are utilized in various products in the shopping mall. We already have seen, and these are very efficient system. RFID system is very efficient system compared to the normally utilized devices, which are used for finding out the products. So RFID tags, why it is important? Because if someone is reaching with RFID device to some floor, if the device is on, within a fraction of second, all the data of the floor can be read by the RFID device. So such a efficient system also uses microstrip antenna, in which it is utilizing the frequencies from at 30 hertz as well as up to 5.8 hertz, 5.8 gigahertz. So that is why this range of frequency is also compatible with the microstrip antenna design. And we already have seen that there are various types of research papers also available on RFID, and products are also implemented. Now, this is the WiMAX worldwide interoperability for microwave access. The IEEE 802.16 standard is known as the WiMAX. It can reach up to 30-mile radius theoretically, and data rate up to 70 Mbps. So these are the theoretical values. Microstrip patch antennas also generate 3 resonant modes, that is 2.7, 3.3, and 5.3 gigahertz. Also, it is available for the radar applications. So we already have seen that radar is very much useful for tracking object. And here is also the application of microstrip antenna is available. And it is of great importance because the radar we have seen, normally it is constructed with a large dimension, but as microstrip antenna is possible with small dimension. So in a miniature devices, also radar application is possible. So if any mobile device is incorporated with such microstrip antenna, the radar application could be installed in small miniature devices. Retina application is also another important part of the microstrip antenna. It produces a specific, it gives us a specific feature, which is a rectification of the receive signal and converting it into DC power. So retina is also acting as a power source for any mobile devices. Now, the microstrip antenna design initially has been thought of for two purposes. One is the compact antenna, another is the broadband antenna. So initially, before 2000, we have seen that there are various research papers which has been constructed on compact antenna design. And after 2000, we have seen that gradually the broadband antenna design has been of great importance because of the invent of the monopole antenna design we will discuss today, in which the broadband antenna has been now possible, and it has crossed the limitation of the low bandwidth, which was available for high Q resonator action in microstrip antennas. Now, regarding the compact sorted microstrip antenna, these are the typical structures shown, in which it is showing that a circular patch, or it is a semicircular patch or a quarter circular patch. So these are all having some sorting pin. That is, these are the sorting pins which are at a radial distance x from the origin. So if we use such sorting pin, that means if there is any short circuit connection between the patch and ground plane, the available radiation frequency for the conventional antenna could be reduced to a lower frequency. And that is why if the frequency is lowered, then the larger wavelength dimension is possible to implement in small size of antenna. So conventional antenna shows some frequency which could be reduced to a lower frequency using such shorting pin configuration. So this is one of the method of several methods to make an antenna smaller. And this is also typically a shaped microstrip antenna in which the current path has been meandered, so that the H-shaped microstrip antenna or shorted H-shaped microstrip antenna are showing some possibility of reducing the size of the microstrip antenna. So here H-shaped means here the current path has been meandered, so it is traveling larger distance compared to the conventional microstrip antenna of the same dimension. That means here whatever is the dimension is taken, W is the width and L is the length. If we take the conventional rectangular shape, the length of the current, that is path length of the current, was something. But if we make such typical shape where part of the rectangular microstrip antenna has been etched out, so this in this portion there is no copper, so that is why current has to travel a curvilinear path, which is showing that the path length of the current has been increased, and that is why a larger wavelength is possible to implement in this smaller dimension. Okay, so that is why the frequency may be reduced, because wavelength is increased means the operating frequency has been reduced, and that is why we can realize such microstrip antenna. That means a reduced size microstrip antenna. So this is one of the feature of reducing the size of the antenna. Now here it is the broadband gap coupled shorted rectangular microstrip antenna. So RMSA stands for rectangular microstrip antenna, where it is showing that a rectangular size was the conventional size of the microstrip antenna in which the gap is created. So on the left hand side, the feeding point is available, and on the right hand side, there is no feeding point, but it is a parasitic patch on the ground. So it is the patch side which is shown by two number of rectangles. On one side, if we see this point here, it is the feed point, and on the left hand side here it is the shorting part, and on the right hand side also here is the shorting part. So these are the shorting point which is effective to reduce the size of the microstrip antenna, as well as it is producing the broader bandwidth. So this gap, which is shown by S is the gap between two number of rectangular patches. So if S is varied, the width bandwidth may be increased, so we can get broadband antenna. Normally, the definition of the broadband antenna is more than 10% of the bandwidth should be more than 10% with respect to the center frequency. And here is the typical presentation of a rectangular microstrip antenna with several slits created on the rectangular patch. So this is nothing but to increase the surface current path, and that will lead to the reduction of the resonant frequency, as we already have discussed. And this is a typical example where the feeding point is located here, and from this, when the current is traveling towards the end of the patch, it is traveling several curvilinear paths. But at the end, if we see, there is a large rectangular slit which is present here. Sometimes this type of slit reduces the power which is required to be radiated. And one more thing we need to notice in such configuration, that the feeding point is on one side, not at the origin, but it is taken at one side. So therefore, the path length here, it is smaller at this end of the patch, but on the left hand side, the path length is larger. So where the path length is larger, it is responsible for reduced operating frequency. That is, the lowest resonant frequency is possible for the current which is traveling towards the left hand side of the patch. And if the current is, if we consider the current which is traveling towards the right side, and that will be responsible for higher resonating frequency. Also, there are several other paths through which the current is traveling. That is why, if sufficient amount of power is radiated in a particular side of the slit, then we are getting some resonating frequency. So everything depends on the required amount of power. We will discuss about the resonant frequency at the time of the results and observation. So here is also more examples of the gap coupled broadband circular patch microstrip antenna. So all these techniques are responsible for either bandwidth or the reduction of the patch size. So these are several types of similar microstrip antennas with different features. And here it is a stacked broadband circular patch microstrip antenna. So here is also the bandwidth may be increased. So stacked means several number of dielectric material which has been stacked so that the bandwidth could be increased. And here is the aperture coupled broadband circular polarization microstrip antenna. So here many features has been introduced. So aperture has been coupled. So there are two number of apertures which are coupled so that the amount of radiation may reach the bandwidth to be larger. That will reach more than 10% of center frequency bandwidth, as well as it is producing circular polarization. So therefore, all these features could be introduced with such microstrip antennas. Now, regarding the recent investigations on microstrip patch antennas, we will discuss these points now. So first is antenna size reduction. So there are some typical results which has been found in the laboratory that depends on the antenna size reduction, parametric study of the absolute gain, as well as rectangular slot antennas, broadband monopole antennas, how we have designed the monopole antenna, as well as their radiation pattern, return loss, parametric studies on absolute gain, ultra wideband feature, how it has been incorporated in the microstrip antenna, as well as the monopole microstrip antenna design for ultra wideband characteristics, parametric studies, microstrip antenna design with study of the effect of the substrate. So that is also typical study we have carried out, that effect of substrate may influence the impedance bandwidth. Therefore, and finally, the graphical analysis of the impedance bandwidth due to the substrate to patch area ratio. So here is the typical equations which is normally used for reduction of the size of the microstrip antenna. That is, if we need to reduce the size of the microstrip antenna, we need to reduce the operating frequency. And for that purpose, these equations are very much effective. So LE stands for the effective length, and delta L is the small increase of the length of the microstrip antenna, and WE is the effective width of the radiating patch. Delta L is the fractional length which is required to be calculated with respect to the thickness of the microstrip antenna. That means microstrip antenna is fabricated on a PCB. The PCB is might having some height, so that height is represented by this small h, and the effective dielectric constant is epsilon e. So here is the typical relation between the resonating frequency and all these parameters at the bottom. And the effective dielectric constant, as we discussed, here is the equation. Epsilon e is the effective dielectric constant, and W stands for the width of the microstrip antenna. So these are the equations which are normally used for the generation of the microstrip antenna with reduced size. So these are typical equations. I'm not going to discuss all these equations here, but I'm showing that these are typical calculations which may be made for the microstrip antenna with reduced size. That is, size reduction is required if required. So these equations are effectively used. So these are typical microstrip antenna. This has been designed at our laboratory. Here, a typical rectangular patch antenna has been created, which has some radiation at certain frequency. And later on, so it was showing that it was generated with 5.5 gigahertz radiating frequency. The length was 16 millimeter, width was 20 millimeter. It was a PTFE substrate with 2.4 dielectric constant, and the height is typically 1.5875 millimeter, though we are telling it is 1.6 millimeter, with the radiation pattern shown here. Now we are going to reduce the size of this antenna. So to reduce the size of the antenna, those equations which we already have shown, we have used, and we found these results. So here for antenna 1 structure, which is the conventional antenna, we got the 5.576 radiating frequency or radiation frequency, for which the return loss received was minus 19 dB, and approximately minus 19 dB, and the minus 10 dB bandwidth we received 177.6 megahertz, which was a narrow band, because if we take the ratio of 177 with respect to the 5.576 gigahertz, it is not 10%. So here all other reduced size, that is, size reduction has been possible by creating two number of slits. Here it is showing that L1 and L2, which are the two number of slits of same dimension, 10 by 1 millimeter. Here is also 10 by 1 millimeter. And another slit is created L3 on the right hand side, and two number of small holes has been created at the top and at the bottom. So all these has been possible to produce the reduced frequency of the resulting antenna. And if we see the carrier frequency, hello.
Hello.
Is it audible?
Yeah, audible, sir.
Audible, sir.
Audible.
Here, the frequency has been reduced by creating the slits in the radiating patch and the small circular holes which are present at the top and bottom, which are sufficient to give us the improved return loss. Because if we do not create this small circular hole, we cannot get sufficient amount of return loss. And here, the first resonating frequency occurred at 3.487 gigahertz, and the second resonating frequency is at 4.481 gigahertz. The third resonating frequency is at 4.61 gigahertz, and the fourth one is at 5.725 gigahertz. So all these resonating frequencies created due to the presence of such rectangular slits. And also, if we see the frequency ratio, which is the frequency ratios are sufficient, very showing these are very much acceptable. That is, F2 by F1 is 1.29, F3 by F1 is 1.32, and F4 by F1 is 1.64. All these frequency ratios are very much satisfied value, because F2 by F1 or F3 by F1, if these values are less than 1, then we cannot get such satisfied result, which we have found that 3.487 gigahertz is the reduced resonant frequency. And these are the typical radiation pattern which has been found from the same microstrip antenna. That is 3.487 shows the power which is created due to the slit. That means this is the power distribution of the current which is propagating in the microstrip antenna. So here at the end, at the edge of the slit, we are finding sufficient amount of current which is producing the power for the radiation of the signal. Similarly, for 4.481, a dense power which is observed at the edge of the slits. Similarly, at 5.725 also we are finding. So more is the density of the current, we are getting the reddish part of the current path length. And here is the parametric study of the microstrip antenna, where we are finding that L1, L2, L3, all these three dimensions, and which has been studied separately. So L1 studied here with 0 millimeter, 3 millimeter, 7 and 10 millimeter at the top to find out several values of the return loss. And for the middle one, it is for L2, and the lower one for L3. So such different studies has been carried out to compare which value of L1, L2 or L3 is good for reducing the frequency of the microstrip antenna. And on the right hand side, we are seeing that absolute gain which has been plotted with respect to the frequency. And it shows that absolute gain are sufficient at 3.5 gigahertz as well as around 4.5 gigahertz. So here absolute gain is ranging for more amount of frequency range, and also at 5.8 gigahertz we are finding sufficient amount of microstrip antenna. So these are the points at which our proposed microstrip antenna is applicable, because if we have sufficient amount of gain in those frequency, the microstrip antenna will produce a sufficient amount of radiation. Now, thereafter, some salient observation which has been found from those antennas, that is the slot length and width are controlled to increase the current path. So this is one of the salient observation, because if we do not control the slot length, then the current path may be increased, but the amount of radiation may be decreased. The addition of the circular slots in the patch improves return loss, as we already have discussed, and the size of the reduction of the frequency is received approximately 64%, and this could be increased further if we give attention to the current path length. The radio size antenna shows wide beam width, that is a 3 dB beam width, and with increased frequency ratio and the multi-frequency operation. Now, these are the discussion of the broadband monopole microstrip antenna. In 1895, the person who has invented this monopole antenna, his name is Guglielmo Marconi. But at that time, it was not efficient because it was utilizing broader spectrum for the small amount of power. So it was a kind of a very broad spectrum with low bit rate. So that was a bad utilization of the power, and that is why less important for long days. Later, before around 50 years, it is getting again more importance because when we are interested to increase the bandwidth, at that time the monopole antenna is again a matter of interest for researcher. The primary focus was on impedance mismatch, such as the configuration of the ground plane and the patch may be focused. Also, on the substrate selection, that means the thickness and dielectric constant are again another important factor for the bandwidth. And also another focus was given on the feed line orientation, that means whether it is a H feed or it is a pro feed microstrip antenna. And the benefits of the large bandwidth are the high data rate. That means if we increase the bandwidth of the microstrip antenna, then the data rate of the microstrip antenna may be increased. And this is very much required in today's communication system because gradually the data rate requirement is more and more by the users. So that is why high data rate is possible using such monopole configuration in the microstrip antenna. The robustness to for the propagation of fading, that means sometimes the signals are fade away, but for the monopole antenna it is producing sufficient gain so that the fade away signals may be recovered, that means fade away signals may be restricted. Accurate ranging and geolocation is also possible. Superior obstacle penetration, resistance to jamming, interference rejection, minimum interference with narrow bandwidth system. And here are the construction of the monopole microstrip antenna, which is showing that there is a small amount of gap which is maintained between the patch and ground. And here the design has been made on one side ground and another side is patch. So rectangular microstrip antenna is again utilized with small amount of impedance transformer, and there is a microstrip line. So here in the bottom, the M3 shows the dimension of the microstrip feed line, and thereafter L1 is the dimension for the impedance transformation. That means impedance may be transformed using the small amount of dimension. So if we vary the thickness of this impedance transformer, the amount of radiation may be varied, and it may happen that sufficient amount of radiation may be achieved with a specific value of this impedance transformer. And later on, this top side is a normal patch. Here, nothing is created with respect to the current path length increase or decrease. One thing is important for the monopole microstrip antenna. Why it is monopole? Actually, monopole literally is not maintained because here is also ground plane as well as the line fed to the rectangular patch. So it is not literally monopole, but monopole in the sense that on the backside of the microstrip patch, there is the presence of the ground plane. Okay, so ground plane is present at the bottom side, which is of reduced size. So with a small amount of ground, the patch path length has been increased. So that is why it is termed as monopole. That is, the existence of the ground plane has been negligible. So this is the meaning of the monopole. Otherwise, it is also having two number of lines. One is ground plane, another is the feed line. And here, several dimensions, that means the width of the patch, length of the patch, as well as L1, M1, all these dimensions are written here for the construction of this monopole microstrip antenna, which shows that the bandwidth obtained, the minus 10 dB return loss cut started from this point, which is approximately 4.19 gigahertz, up to 7.36 gigahertz, we got the minus 10 dB return loss. So therefore, it is a wider bandwidth, and here we have noticed that it is 54.9% bandwidth with reference to the average frequency between 4.19 and 7.36, because if we take the average of these two frequencies, we can get the center frequency, with respect to which we got 54.9% bandwidth. So therefore bandwidth here calculated 3.17, and if we take the ratio of this bandwidth and the center frequency, we get the percentage is 54.9. On the other hand, we can say that the center frequency, if multiplied with 54.9, we can get the bandwidth is 3.17 gigahertz. And the lowest return loss obtained is minus 28 dB. Similarly, for 2.43 gigahertz bandwidth, we got the lower cut is at 8.695 gigahertz and the upper cut is at 11.125 gigahertz. So there is also another range of frequency for which we got this wider bandwidth, and that is 24.52%. So therefore, dual frequency application is achieved using such monopole microstrip antenna design. And now this is a typical surface current distribution for the microstrip antenna, which is discussed. So here, the monopole microstrip antenna is showing that the current path length, which is propagating through the impedance transformer to the microstrip patch, which is showing that sufficient amount of power is distributed towards the edge of the microstrip patch, that is at the bottom, and at this side, sufficient amount of power is distributed, so which is responsible for the radiation, as well as in the ground plane also we are finding the amount of power is considerable at the top edge of this ground plane. So so there are two frequencies shown. One is at 7.28 gigahertz, another is at 10.54 gigahertz. And these are the typical radiation pattern which is shown for the monopole microstrip antenna at 6.01 gigahertz and at 10.6 gigahertz. And here the observations are the good agreement between the simulation and measured radiation pattern. As we already have seen, the return loss is also shows very good agreement with the theoretical study, though it is not exactly similar because of some losses which are incurred in the microstrip patch antenna. That is why it is not exactly similar, but it is showing some good agreement. And the minus 3 dB beamwidth is obtained around 90 degree at 6.01 gigahertz, as well as 85 degree at 10.6 gigahertz, so which are also sufficient for a broadband microstrip antenna. Now, this is the parametric study of the and the absolute gain of the monopole microstrip antenna. Return losses are shown on the left-hand side, and the corresponding microstrip patch antenna, which is monopole microstrip antenna, shown on the right-hand side. Several parametric studies has been carried out depending on some configurations such as M5 and M2. As shown, M5 is the gap between the ground plane and the bottom edge of the radiating patch, and M2 is the width of the impedance transformer. So if we take some variations or combinations of the M5 and M2, we can get several values of the lowest minus 10 dB frequency, which is varying from 5.04 to 8.68. So therefore, we should go for the lowest frequency, which is 5.04, with M5 equal to 1 millimeter and M2 equal to 2 millimeter. So this M2 is equal to 1 millimeter. So both are 1 millimeter. So here one thing is notable, that the gap between the bottom side of the radiating patch and the top side of the ground patch and ground plane, this distance should be reduced. Otherwise, we cannot get sufficient amount of reduction in the lowest frequency. And also we need to be we need to be careful about the percentage of bandwidth, which is received 39.14% at the top side, and gradually it is falling. But here 40.33 is also acceptable. So if we increase M2 from 1 to 2 millimeter, there is no much change in the percentage of bandwidth. But if we go for M2 equal to 3 millimeter, the observation shows that the bandwidth, that means percentage of bandwidth, has been reduced to almost half, 23 gigahertz. So this is one main thing to note here. And another thing is that similar 40 gigahertz bandwidth is also available here. 42.4% of bandwidth we have received with increased M5 and increased M2. But the problem is that the center frequency, or the lowest operating frequency, has been increased by 2.81 gigahertz, because earlier we have received 5.04 gigahertz, Now it has been increased to 7.81 gigahertz. So these are the points we need to be careful whenever we are designing microstrip antenna for broadband applications. Now here are the observations on the broadband antenna design. Monopole antenna dimensions are optimized to achieve the broadband operation. So here for last 10 to 15 years, this is of great importance. This research is of great importance because the bandwidth is possible to increase for microstrip antenna with such monopole configuration. Smaller value of the gap between the radiating patch edge and the ground plane reduces the first resonating frequency but increases the frequency ratio. Adjustment of width of the connecting impedance transformer between patch and the microstrip feed line frequency ratios have been reduced, and closer frequency and closer resonating modes may widen the operating bandwidth. Now this is the ultra wideband antenna design. In 1910, Hodge invented wideband system by means of the spark gap generator. So this spark gap generator was a broadband system, but it was utilizing a very low data rate. So that is why it was not getting importance. But later on, we have found that the importance has been increased because of the high data rate system is also possible to implement using the same spark gap generator. So this exploitation of the signal spreading was unknown at that time. The interest in UWB system was received in the year 1960 by military research radar community for improving the accuracy. The accuracy increases as the width of the transmitted pulse is reduced, and hence the increasing bandwidth. The problem of multiple access interface of unsynchronized users remained and unsolved by time hopping impulse radio in the early 1990s, and it was made by Wynn and Skolch. In 2002, FCC permitted the international UWB emission in the frequency range between the 3.1 to 10.6 gigahertz, subject to the certain restrictions for the emission of power spectrum. Now, this is the comparison. The wireless local area network, which is showing that at 5.725 to 5.825 gigahertz, it is available with very high gain. And the ultra wideband range of frequency starting from 3.1 to 10.6 gigahertz is encompassing this wireless LAN frequency, but still it is not objectionable because of the dot lines shows that the amount of power radiated by the ultra wideband system is very small compared to the wireless LAN microstrip antennas or wireless LAN systems. So that is why if at the same area wireless LAN is available, such ultra wideband application is also acceptable to increase the data rate. And here is the configuration of the monopole microstrip antenna design for the ultra wideband characteristics. Various dimensions shows with the thickness of 1.6 millimeter of PTFE substrate and the dielectric constant taken 2.4. So here in this design, if we see that the edge of the monopole microstrip antenna has been cut out only to improve the return loss. So one important thing for the monopole antenna design is that though the bandwidth is very large, it shows the amount of power is degraded, and this degradation of the power of radiation need to be emphasized by several techniques. So such technique is creation of bevel at the edge, at the corner edge. So this corner has been beveled and this corner is also beveled. So that is why the return loss has been improved. Therefore, the antenna measured and antenna simulated, if we compare, they are showing the good agreement. So that is why the measurement is almost following the theoretical value. And here we are getting the 9.2 gigahertz bandwidth with the percentage of bandwidth is approximately 128%. And this is a very wide bandwidth as compared to the microstrip antennas, which was available earlier, which are of narrow band microstrip antennas. So here the lower cut frequency is 2.59 gigahertz and the upper cut frequency is 11.79 gigahertz. And with some parametric study, we can align the lower cut and upper cut as defined by the Federal Communication Commission, FCC. Now, the corresponding radiation shows by these surface current distributions of the microstrip antenna, and the density of the power is also shown. Now, one thing to note here is that we have utilized this small rectangular strip. This is not the patch. We cannot say this small rectangular narrow strip, though here it is not small, it is larger compared to the rectangular patch, but the thickness, the width is small. That is why you are telling it is a narrow rectangular strip. And at the bottom of this strip, at this point, there is a shorting pin which is connecting the ground. And this is of great importance to reduce the lower resonating frequency. That means that means around 2.59 gigahertz, the resonating frequency received. This is responsible only due to this narrow rectangular strip, which is prepared here. And also the gap between the strip and the rectangular patch requires sufficient amount of gap. Otherwise, the bandwidth as well as the return loss will not be acceptable. Now, these are the various parametric studies carried out with the dimensions D, which is showing that if it is 0.5 millimeter, we are getting the bandwidth approximately 8.35 gigahertz, and the percentage of bandwidth shows 120 gigahertz or 120% bandwidth. Similarly, for D equal to 1 millimeter, we are not getting much difference in the percentage of bandwidth, but the amount of bandwidth has been increased to 9 gigahertz. And for D equal to 2 millimeter, the bandwidth has been reduced substantially. It is 3.77 gigahertz with the percentage of bandwidth 74%. So also Q is another dimension for which a parametric study carried out. So this is the rectangular strip, which is showing that if it is 7 millimeter, we are getting 85% bandwidth with the lower cut of the resonating frequency is 4.6 gigahertz. Whereas if we increase the Q with 20 millimeter, so if it is reaching 20 millimeter length, as it is shown with the bold, because at 20 millimeter, we are getting the lower cut much reduced to 2.75 gigahertz with acceptable return loss. And also several parametric studies carried out here. This is the radiation pattern with 5.57 and 10.7 gigahertz. And these are the typical observations found in case of ultra wideband antenna design, in which we found that return loss of upper cutoff frequency in UWB is greatly depending on the small gap between the radiating patches and ground plane. Increase in ground patch gap may improve impedance bandwidth in higher frequency at the cost of poor return loss in UWB frequency range. The return loss of resonating mode is controlled by the dimensions of two corner cut bevels. So this is one of the important feature which has been incorporated in this microstrip antenna, that means in this monopole antenna, that is creation of the bevel. Without this bevel, we may not get the sufficient amount of return loss. And if it is not sufficient, then the resonating frequency will not be acceptable. So lower cutoff frequency in UWB is controlled by the length of the grounded strip, as we have told that the dimension Q is fully controlling the lowest frequency of the ultra wideband microstrip antenna. And all the measurements show good agreement with the simulation result. We already have compared the simulation result with the fabricated microstrip antenna when it has been measured. And these are another study of the microstrip antenna. Here the variation in the substrate dimension has produced some result which may be highlighted. So many dimensions are shown, but if we see the characteristics, now it is clear that the theoretical study and practical study are very much related. And it shows that the sufficient amount of reduction in the lower cutoff frequency is possible. As well as we have reached a very large amount of bandwidth. And these are typical surface current distributions. And these are typical data. We have marked bold for the notable observations. That is minus 10 dB bandwidth has been reached 23.83% with the substrate dimension, that is substrate to patch area ratio. If it is 31.96, if it is reduced, the amount of percentage bandwidth is not acceptable as broadband antenna. So there are several configurations of the antenna 1 and 2 has been studied to find out whether it is a broadband antenna or increased bandwidth antenna. And some graphical characteristics has been plotted. Here the substrate area to patch area ratio was compared with the maximum minus 10 dB bandwidth, and is showing that it is gradually falling with respect to the patch ratio. That means more is substrate area to patch ratio, we are getting a reduced percentage of 10 dB bandwidth. So it is showing a very linear relation between them. And maximum minus 10 dB bandwidth, if compared with the center frequency, we are getting this type of characteristics for the two number of antennas we have compared. And these are the typical radiation pattern for the antennas. These are the gain plot, which is showing that somewhere the gain has reached the maximum value at certain resonating frequency. And these are the salient observations. That means the reduction of the ratio of substrate area to the patch area may enhance the impedance bandwidth. Return loss may be improved by reducing the gap between the patch and ground plane. Minus 10 dB bandwidth is increased when the substrate area to patch area ratio is decreased, and also the decreasing the same ratio, the center frequency is decreased. So thank you.
If any participant they can pose that questions. If any participant have any questions.
Hello, sir.
Hello.
Hello. Hello.
Hello, sir. Good morning. Hello, sir. Good morning. Hello. Hello.
You
Can I speak, sir?
ask the questions, friend.
Yes,
you can speak, sir.
Sir, can I ask, sir?
Yes, you can ask, sir. Yes, you can ask.
Good morning, sir. Good morning. Thank you. You explained very excellently, sir. Really, we are happy. And I want actually CPW structures. I designed multi-frequency antenna, sir. Sir, multi-band operation. We should get all gains are in positive or negative, sir, because some getting negative, some getting positive. Hello? Hello?
Sir, your mic is muted. Sir, your mic muted.
Yes. The gain depends on the scale. If you take typical scale, it could be negative, but normally gain is positive.
For all frequencies, we should get positive, sir.
Yes, if you take the gain in decibel or like that, it could come negative, but normally the gain is positive.
That is true, but I should get all positive. Okay, sir.
But thing is that
Thank you,
for
thank
which frequency range you are interested, that is one thing.
For that, okay, sir. For that, okay, but other frequency sides, I'm getting negative, sir. That is the problem.
Okay. Which software you are utilizing?
FR4, sir. FR4.
Substrate. Okay.
FR4.
And the simulation carried out?
HFSS.
HFSS. Okay.
Yes, sir.
You need to check the particular configurations because in HFSS several settings are there. So please check those settings if okay or not.
And one thing I observed, sir, if I change radiation box dimensions,
okay.
If I change the radiation box dimensions, I will get little improvements, sir. But not in all.
Sure.
Not in all.
Yes. Yes, that might happen. Actually, I'm telling that sometimes the idea of the microstrip antenna is taken wrongly. That is, whatever cut we are making, we are expecting that we are getting some good result. Sometimes it happens. So at that time, I think that some literature survey should be carried out by everyone before going to design. Because otherwise, what will happen? It will consume time. And today, time is important. If we go for a typical cart, we need to be careful whether it has been earlier observed or not. Okay, there are many good review papers are there. If you go through those review papers, it will give those ideas that whether the particular cart will give you sufficient amount of bandwidth or not, whether the range of frequency for which you are interested, it is possible or not. So if those things you take in consideration, then if you go for further cart, then you will have this knowledge that whether the cart will be appropriate or not. Like that.
Okay, sir. Thank you. Thank you. Nice talking with you, sir.
Sir, I have
one next question is there. Hello,
sir. I have
sir.
a question.
Sir, what is that the difference between broadband and ultra wideband antenna?
Yeah, that's a nice question. Broadband antenna and ultra wideband antenna are nothing but I can tell one is parent, another is son. Like that, broadband antenna is defined as the ratio. That is the percentage of the bandwidth with respect to the center frequency. If it is more than 10%, then it is known as broadband antenna. That is the earlier definition of broadband antenna. And the ultra wideband antenna was given by FCC. That is the Federal Commission. They have defined that 3.1 to 10.6 gigahertz is the ultra wideband antenna. And it was designed because of the high data rate which is required by present day communication system. That is why ultra wideband definition was very much important, because earlier broadband antenna has reached certain level of research in which the collision of those bandwidth with the existing commercial frequencies was happening. To reduce such clash, this definition of the ultra wideband was defined by FCC.
And sir, another one question. Can the partial ground and defective ground give high bandwidth?
Yes, surely. Surely, a partial ground means sometimes monopole antenna is considered as partial ground. Actually, the definition is that the ground plane is reduced. So monopole is literally not implemented here. Monopole means what we are thinking, that only one line is possible, another reference plane is absent. This is not like that. the ground plane is present, but the length of the ground plane has been reduced. So that is why you are telling it is monopole. That is, existence of ground plane has been diminished. So that is sometimes called partially ground plane. And for the defective ground plane, it has some typical structure. If you go through the papers of Dr. Debatosh Guho, he has done extensive research on this defective ground plane. I am again repeating, Dr. Debatosh Guho of Calcutta University. If you go for the paper with Dr. Debatosh Guho written, you will have extensive idea on this defective ground plane.
Sir, I have a question, sir.
Ask, sir.
Sir, suppose I have a antenna of bandwidth from say 5 to 12 gigahertz, and if I want to shift the lower frequency from 5 to say 2 gigahertz, sir, how can I do that, sir?
Yes, it is possible by creating slots. That is, in the microstrip antenna, if we create some slot, the path of the current may be increased. And once the current path is increased, the wavelength is also increased. So therefore, the higher wavelength could be implemented at lower dimension. That is where we are getting lower frequency.
Sir, another one question. How to provide pins on patch in software to sort that the ground for getting enhanced bandwidth? Means any software is possible to given any pins?
The voice was cut. Please repeat.
How to provide the pins on patch in software to increase the bandwidth?
Okay, that is location.
Location.
Locations. How to provide the locations? Okay, so there are options in the software to provide the location. But if you want to forecast about the point, that is in which point it will be beneficial to provide the feeding point, that depends on the advanced version of the software, because there are some software in which nowadays, if you give the curve, it can design the patch, and the variation in the patch is also possible. Yes.
And sir, what is the parameter for assessing any broadband antenna?
Okay, there are several parameters for broadband antenna. That means one parameter I already have mentioned in case of my PPT. If you have observed that there is a gap between the patch and the top edge of the ground plane. If this gap is reduced, then the bandwidth will be increased. We already have shown in our study. As well as there is a shorted, there is a microstrip one parasitic length, which I have shown with dimension Q, if you notice in my presentation. So if that length has been increased, then also the lowest frequency could be reduced, and therefore the bandwidth is possible to increase.
Hello, sir.
Hello.
Sir, I'm just carry forward whatever the message that I have written there. Actually, what I wanted to know, if suppose we are using that pins just to short the ground and patch, just to enhance the bandwidth. So on the hardware, means do we drill the hole and then insert the conductor in between the patch and the ground plane, or is there some other methods available? And what kind of things are available also in the software? That is what I am asking.
Actually, your voice was breaking. Some noise is coming.
Am I audible, sir?
That is why. Yes, you are audible. But what happened? Some noise has come, and sometimes I have not done.
Actually,
Sir, now you mute and you can ask. Sir, now you mute. Tapan sir.
Okay.
Mute
Yes,
and you ask that.
Sir, my question is suppose we wanted to enhance the bandwidth, and for that we can, let's say, shorted the patch and ground by using the pins. Okay, so on the hardware, means once we have fabricated our patch antenna design, so how can we provide these pins just to short the patch and the ground? Is it just by drilling the hole and inserting conductor in between this two, or something else?
Yes. As I understood that shorting pin, the technique of shorting pin you are asking.
Yes,
How
sir,
to
yes.
use the shorting pin. Yes,
Yes,
technique for
both
shorting
on the
pin.
hardware and the in software.
Yes. Yes. With a layman idea, what you have told, it is okay. If we drill it and with some certain amount of conductor, if we insert and on the both side, if we shoulder, then it may provide, but it will give substantial amount of losses. The losses which is providing by this technique may not be sufficient for commercial application of microstrip antenna. So that is why what we go for, we are going for a typical technique known as PTH technique in PCB design. PTH stands for plate through hole. That means if we create a hole using a normal drill, that means a 0.5 mm drill or 1 mm drill, we can create a hole. But through the hole, a PTH, that means plate through hole, if passed, and the quality of plate which is passed through the hole should be good enough. That is, it should be a good conductor so that the loss could be minimized. You got my point. That is PCB
sir,
design technique has some plate through hole technique. If you search in Google PTH technique in PCB design, you will have this idea. And what my suggestion is that this PTH is possible by any vendor can give you PTH, but you have to go for those PTH which is giving low loss PTH connection, because vendors are very much familiar with the production in which low frequency constructions are there in our area, but high frequency are having low demand. That is why they are not sometimes careful about the quality of the conductor which is passing through the PTH. So that is why we need a quality conductor to be passed through.
Okay, just to avoid the losses.
Yes.
And
Sir,
what
another
about,
one.
sir, on software? Just last answer, sir. Last question. Can you suggest us on software how to provide these pins? Maybe on ADS or HFSS software.
Okay. The software which is good for this simulation, you are telling?
Yes.
Okay.
No.
HFSS
Sir,
is.
No. I'm asking same thing, like okay, on hardware with the help of that drilling and all we can do that, but in the software means how can we provide that pins on the software just to short ground and our radiating patch.
Okay. So there is a creation of holes using the software. If there is a creation of hole, you also have some option of filling the hole. Okay. So if you do not fill, it will be a normal hole, and if you fill it with a conductor, so there is also option. That is whether it will be filled by conductor or not. So if it is filled by conductor, then it is shorting both end.
Okay, fine. Thank you.
Yeah.
Sir, can anyone increase the bandwidth in X band by stacked microstrip antenna?
Yes, it is possible. I cannot say that it is impossible, but the type of design has to be thought out.
So what is actually stacked microstrip antenna?
Stacked microstrip antenna is nothing but layer by layer the microstrip plates are given, and in between the two number of PCBs, either there might have foam or there might have little amount of dielectric material or etched plane. That means the copper has been etched out. It may be happening. Okay, using some typical technique or gum pasting, we can create such microstrip antenna. But it is a complex design.
Okay.
Sir, how
Can
to
any
design how to increase the axial ratio of any microstrip edge antenna?
That depends on the design of the circular microstrip antenna. We already have discussed the techniques for the circular microstrip antenna, in which sometimes multiple ports are also utilized. And once you are getting the axial ratio more than 10 dB, then you can expect it is circular microstrip antenna. Then circular means circular
more
polarization.
than 10 dB or 3
is
dB?
possible. Yes, yes. It's more than 3 dB, right? It is more than 3 dB.
So if I want 8 gigahertz or 7 gigahertz axial ratio, it is possible?
See, the percentage of bandwidth you need to calculate. So 3 dB cut you have to find out. Normally it is of the order of megahertz axial ratio.
No, sir, I'm talking about the axial ratio bandwidth, sir.
Yeah.
Impedance bandwidth, sir. Near about impedance bandwidth with axial ratio.
Yes.
Sir,
So it is
sir, one small
2
question.
knots. You are thinking. Yes.
Sir, one small question can I ask, sir?
Yes, yes, you can ask.
Continue.
Sir, we are considering impedance bandwidth, no, sir. From bandwidth calculation, we are considering only impedance bandwidth. Why don't we consider from VSWR characteristic also, sir? It is.
Yeah. We can. No harm. Yes.
Generally in papers, they mentioned only impedance bandwidth. So even though we are getting better bandwidth in VSWR character less than 2.
Yes, if we go for yes, right. That is also represented in various papers. So that depends on where you have measured. If you have measured on a device that is network analyzer, then you are very much familiar with return loss. That is S11 parameter. That is it is easy to calculate. Also, you can calculate such impedance bandwidth from the impedance characteristics as well. That is where the RZ characteristics I am telling. Because this impedance bandwidth, that is a resonating frequency, to study the resonance frequency, there are several parameters, not only Z parameters, Y parameters is also available. If you go for the Y parameter, there is also, it is possible. But that depends on the device you are familiar and you are finding it is suitable to calculate. That is why we are going for such S11 parameter mostly.
Okay,
sir, one last question. How to identify polarization pattern from surface current distribution?
Normally, that is a visual observation. So better if we go for the mathematical value, then a numerical value, then it will be more effective.
Okay, sir.
Thank you.
Thank you.
Sorry, sir, one more question from me, sir.
Yes.
Sir, myself, I am M. Krishna Chandakeshwara from Vignan University, sir, and it's a really wonderful session. And here I have a small doubt, sir. Generally, for most of, sir, am I audible?
Yes,
audible.
Yes, sir. Generally, for most of the applications, we need a narrow bandwidth only. For example, if you go for the applications like WLAN, so the frequency bands around 2.4 to 2.4 to 2.44, and if it is a 5 gigahertz band, the frequency channel spacing is only with 20 megahertz only. So in most of the papers for these specific applications, they are telling narrow bands are sufficient, and what is the need of going for a wider bandwidths and all. So even though with the wide bandwidths we are getting high data rates and all, for most of the applications those wider bandwidths are not required because the channel spacings are in megahertz ranges only. Then in that particular scenario, what is the need of going for these ultra wideband antennas?
Right. You have uttered the problem nicely. That is an excellent question. What you have asked, that why should we go for ultra wideband? There are various narrowband applications are also there. So that depends on the specific reason for which you are interested about designing the antenna. Suppose you are interested for the narrowband antenna design. At that time, why should you go for the ultra wideband antenna design? So that depends on the specific application you are getting the job. That is, you want this much frequency for which you are interested, and you are going for such antenna design. But what happened for ultra wideband frequency definition, that is given by 3.81 to 10.6 gigahertz, it was given only to allow high data rate. That means when the high data rate is required, if you see the width of the pulse is narrower, means the range of the frequency of its spectrum is much wider. So that type of wider spectrum to accommodate narrowband antenna is insufficient. So whenever you are going for such wider bandwidth, that is ultra wideband communication. So at that time, we need such thing. And now if you ask about the data rate, that is WLAN is also providing a broadband. So why should we go for ultra wideband? So that is also another question. And for this answer is that you sometimes you need lower amount of power to be radiated. So when you have restrictions on power, at that time you can increase your bandwidth. And if you have a very high power transmission, such as in case of WLAN, you can reduce the bandwidth. Okay, so that is why I have mentioned the two different situations. One is the amount of power, and another is the amount of bandwidth. Because the gain bandwidth, the product is constant.
Thank you, sir.
Thank you all the participants for that wonderful session by Dr. Indranath Sarkar. And he is my teacher also, and I know a lot of things from that, sir. First, I learned that the microstrip antenna design from that the Indranath Sarkar, sir. And that time, one of my guide, that also sir guide and my guide, he is now not in that the world. That is Dr. Santosh Kumar Chaudhary. He is that the top 10 scientist of India up to that 2000. After that, sir is not continue that work. But we are continue that shared work up to a little bit. We are not that much of good progress of like that, sir. But we are trying to produce some work based on that, sir. And myself, Indranath Sarkar, and lots of students are there, sir. We are working, and we are thankful to that the Dr. Santosh Kumar Chaudhary, who is already late in that the last 6 months before. And also thankful to that my teacher, Dr. Indranath Sarkar, for this wonderful session. And we learned, we gain a lot of things for that session. And also thankful to that the Vignan management and our respected HOD, Dr. Vijay Kumar Urkude, and also our colleagues and all that the department faculty for this event, wonderful success. Thank you all the participants. And again, tomorrow that will be 2 speakers are there. That is very, very highly qualified. One is from Indian Institute of Space Science and Research, Dr. Chinmay Saha, and another one is IIT Ranchi, Dr. Dept Sarkar. So all the participants, I requested that tomorrow session can be started 15 minutes earlier in 10:15 a.m. And we learn a lot of things from that 2 session of that bazaar, because especially Chinmay Saha is design various types of antennas with that IEEE, ITFS, and he is also the coordinator of IEEE chapter, microwave chapter for various Kerala, Kolkata, and everything. He is also that faculty. So better all the participants, I request to join 15 minutes earlier for that wonderful session tomorrow. Today also wonderful session, but tomorrow lots of practical knowledge about how to design, because he is that working in the space science and technology, especially for designing an antenna in the Department of Space. So we know about how in the space antenna we are designed through that his lecture. So thank you one and all to that the participant for today's session is completed. Again, tomorrow we are joined by 10:15. And thank you to all the participants, especially to Indranath Sarkar sir for wonderful session.
Thank you. Thank you very much.
Thank you.
Thank you, sir.